Greetings from BMS College of Engineering, Bangalore. This is the third module in the topic on discrete Fourier transform. Fourier transform or the DFT. We have seen what is DFT and we have tried to appreciate DFT in the earlier modules. Today we shall see how to compute this DFT or DFT, and we shall also take up some properties of DFT. So given a time domain signal x of n, the discrete Fourier transform is given by x of k, and we know that the DFT x of k is given by sigma n equal to 0 to n minus 1 x of n e to the power of minus j 2 pi n k by n, and we can get back the original signal from its DFT coefficients using this expression k equal to 0 to n minus 1 x of k e to the power of j 2 pi n k by n. And let's see how to evaluate the DFT. So in this class, our focus is going to be on computing the DFT and trying to plot the magnitude and the phase spectrum for a few examples. So let's take a simple example to start off. Say we consider, let us say, n equal to 2, and our aim is to compute the 2-point DFT of any given sequence xn. So my xn is going to be of x0, x1. So now one method is to directly use this equation and then evaluate the DFT. So let me take the equation as a first method. Let's try to compute the DFT by using the expression. So what is my expression? X of k is equal to sigma n equal to 0 to n minus 1. Since my n is a 2, n minus 1 is going to be a 1. X of n e to the power of minus j 2 pi n k by 2. So this is my expression that I need to evaluate. Now if I want to evaluate my first component x of 0, so I put k equal to 1 in the above, k equal to 0. I put k equal to 0 in the above expression, and that will give me x of 0. What is that now? Sigma n equal to 0 to 1 x of n e to the power of minus j. But the moment I put k equal to 0, it becomes e power j 0. And hence this is going to be sigma xn. E power j 0 being a 1, it is going to be n equal to 0 to 1 sigma x of n, which is nothing but x0 plus x1. Similarly, now let me put k equal to 1. If I put k equal to 1 in this expression, I can evaluate x of 1. So x of 1, put k equal to 1, sigma n equal to 0 to 1, x of n e to the power of minus j 2 pi n, k is a 1, so 2 pi n by 2, and this becomes sigma n equal to 0 to 1, x of n e to the power of 2 gets cancelled, e power minus j n pi, which is n x of 0, n is 0, x of 0 e power j 0 plus x of 1 e power minus j n pi, x e power minus j pi, n is a 1. So x of 0 and e power minus j pi is a minus 1, and hence this becomes a x of 1. So this is the result we are getting for a 2-point DFT. Or I can write what is the result we have? We have result x of 0 given by x0 plus x1, while x1 is given by x0 minus x1. So this is the result we got by putting the values, by taking the equation and running it from 0 to k and n running from, putting the appropriate values of n and k, we are able to get it. The same result, I can also put it in a matrix form. X of k as say 1, 1, 1, minus 1. And let us say x of 0, say x of 1. So what do I have when I do this matrix multiplication? I get my first term as x0 plus x1. I get the second term as x0 minus x1. So from the equation, we have converted our result into a suitable matrix multiplication. And so to compute any 2-point DFT, if we remember this, this matrix, I can evaluate the 2-point DFT of a given sequence. For example, let's take a small example. Say, so the question is to compute the 2-point DFT of a sequence, say x of n equal to say 2, 4. If I have the sequence xn in this manner, what is my DFT now? It is just and 2, 4, which gives me the first term as 2 plus 4 is 6, second term is 2 minus 4 is a minus 2. As another example of the, say, compute the 2-point DFT of the sequence x of n equal to say 2 plus 3j, 2 minus 3j. So let's take this case. And then what is my x of k going to be? The DFT matrix doesn't change. What changes is my input sequence. So in this case, my input sequence is given as say 2 plus 3j, 2 minus 3j. And what's my product now? The 2-point DFT. This plus this is going to give me a 4. And this minus this. 3j minus 3j is going to be 6j. So this is my example of a 2-point DFT. So computing a 2-point DFT is extremely simple. Similarly, I can construct the matrix for say a 3-point DFT. A 3-point DFT. For my 3-point DFT, what is my x of k is going to be sigma n equal to 0 to 0 is 2 x of n e to the power of minus j 2 pi n k by 3. It's a 3-point DFT. Now a 3-point DFT matrix, if I want to okay, let us say we are giving the sequence x of n as say x0, x1, x2, and then I can substitute the values and get it. So now let me directly try to form the 3-point DFT matrix. Let's take as another example. Let us take say n equal to 4. Let us take n equal to 4. Let's take n equal to 4. So when n equal to 4, so my sequence x of n is going to be of length 4. So x0, x1, x2, x3. So I have my input sequence xn of length 4 and my x of k, the 4-point DFT is given by n equal to 0 to n minus 1. That's a 3 x of n e to the power of minus j 2 pi nk by 4. This is the expression I have. And let us, I can substitute the values and evaluate, but that's going to take a long time. So let us directly try to form the 4-point DFT matrix. the DFT matrix for computing the 4-point DFT. So now here I will try to bring in a notation. Say gamma. Gamma is given by e power minus j 2 pi by 4. And my DFT matrix is going to have gamma to the power of 0, gamma to the power of 1, gamma square, gamma cube, gamma 4, say gamma 5, gamma 6, etc. So my DFT matrix is going to have powers of gamma. So just for simplicity notation, let's introduce this. So what is gamma to the power of 0? E power j 0, so that is going to be a 1. What is gamma to the power of 1? It will be e to the power of minus j 2 pi by 4. Let me take this later. So e power minus j 2 pi by 4, which is e power minus j pi by 2, which is nothing but minus j. Similarly, gamma square. What is gamma square? E power minus j 2 pi 2 by 4, which is e power minus, so 4 gets cancelled, e power minus j pi, and that's a minus 1. Similarly, gamma cube is going to be e power minus j 2 pi 3 by 4, which is nothing but e to the power of minus j 6 pi by 4, which is nothing but plus 3 by 2, so plus j. And let us look at gamma to the power of 4. What is gamma to the power of 4? E to the power of j 2 pi 4 by 4. So this 4 gets cancelled, e power j 2 pi, and that is going to be a 1. What is 1? 1 is same as gamma to the power of 0. Similarly, if I take, say, gamma to the power of 5 is e to the power of minus j 2 pi 5. 5 I can recognize it as say 5 5 5 I will recognize it as say 4 plus 1 by 4, which is nothing but e power minus j 2 pi 4 by 4 and e power minus j 2 pi by 4. And this term is a 1. This term becomes a 1, and then what I'm left with is this, and this we recognize it as e power minus j 2 pi by 4 is same as gamma to the power of 1. Or in general say gamma to the power of m, if I have, it is same as gamma to the power of m mod n. So when if I have any larger number of say for example, if gamma to the power of say 7 will be same as gamma to the power of 7 mod 4, which is nothing but gamma for n equal to. So having seen this, now let us try to construct the 4 by 4 DFT matrix. So x of k is, say, my first row. If I look at my, to compute a 4-point DFT, I need to create a 4 cross 4 DFT matrix. And when I look at the expression, what is my first row? If I see row, my first row k equal to 0. In the second row, k equal to 1. And I have a 2 pi here. And so 2 pi in the first row, k is 0. So n running from 0 to 3. N running from 0 to 3 is taken care of by this vector. So I have my first row as k equal to 0. So gamma to the power of 0, gamma to the power of 0, gamma to the power of 0. Second row, k equal to 1. And so I have it as gamma to the power of 0, 1, 2, 3. Third row, k equal to 2. So 0, 2. So in steps of 0, 2, 4, 6. The last row, k equal to 3. So gamma cube, gamma 6, gamma 9. And by this modulo property, what we find is gamma to the power of 4. Gamma to the power of 4 is same as gamma 0, and gamma to the power of 6 is same as gamma square, because 642 is gamma square. Similarly, this is going to be gamma square. And gamma to the power of 9. So 9 mod 4. We are doing a 4-point DFT. So 9 mod 4 is going to become gamma. So now I have my DFT matrix given in this manner. So let me create the matrix by using this property that we have just now seen. So what we have is, I have gamma to the power of 0. Next, this is gamma square. This is gamma square, and this is gamma. And I have already computed the values of these terms, gamma, gamma square, gamma cube. So to create a 4-point DFT matrix, even though it's a 4 cross 4, the terms are all repeating. So I can create the complete 4 cross 4 matrix for computing a 4-point DFT using only these 4 terms: gamma 0, gamma, gamma square, gamma cube. So all the 16 elements in this matrix are one of these 4 elements, and hence I have my x of k, the 4-point DFT matrix, as first row is all gamma 0, all ones. Second row is gamma, and what is gamma? Minus j. Then gamma square was a minus 1, and gamma cube is plus j. And the second row is same as second column. So this is minus 1 plus j. And then I have my third row as 1 minus 1. Again, third row is same as third column. So I get this. And the last element was gamma, and gamma is a minus j. And this is my x0, x1, x2, x3. So this is what we have as the 4-point DFT matrix for computing the 4-point DFT of any sequence. So let's take an example. Say the aim is to compute the 4-point DFT of a sequence. Say xn is given by 4, 3, 2, 1. So now I want to compute the 4-point DFT matrix, DFT of the sequence. So now I have my x of k equal to, I have to just bring this matrix and I need to multiply it by my input sequence, which is 4, 3, 2, 1. And what is the product? Let's try to evaluate the product. So what's my first element? For all multiplied by 1. So sum of all the elements is going to make my first column. So 4 plus 3 plus 2, 4 and 3, 7, 7 and 3, 10. So my first component is going to be 10. How about the next one? 4. This is 4 minus 3j, minus 2, and plus j. What is that? 4 minus 2, that is 2. 2 minus 2j. And similarly here, the next element I have 4 minus 3, plus 2 and a minus 1. So this is going to be 4 and 2, 6 minus 4, that is a 2. And the last element I have as 4 plus 3j plus 2, it's a minus 2, 4 plus 3j, and then minus 2 and a minus j. So what is this? 4 minus 2, that's a 2. And then 3j minus j is a 2j. So then what I finally have is, when I write my result, I get my 4-point DFT as the first term is a 10. Next is 4 minus 2, that is 2 minus 2j. 2 minus 2j. And next I have 4 plus 2, 6 minus 4, that's a 2. And the next element is 4 minus 2, that's again a 2. And 2 plus 2j. This is my 4-point DFT of the sequence xn, which is given in this manner. Suppose I change my sequence. Let me take another example for computing the same 4-point DFT. Or let me try to verify the result using MATLAB. Let us see whether we have got the right result. So my xn in this case is given by 4, 3, 2, 1. This is my x of n. And I want to compute the 4-point DFT of my sequence xn and a 4-point DFT. So let me verify whether I get the same result. So x of k is given by the 4-point DFT of the sequence xn. And what's my x of k? See, 10, 2 minus 2j, 2, 2 plus 2j. So we get the same result if I perform the sort of multiplication by the DFT matrix. So this is my this is the result. So let's take one more example. Let's take one more example. Say a second example. Now let me consider my sequence xn given by say 20, 4 minus 5j, say 10, 4 plus 5j. And let me try to compute the 4-point DFT of this sequence. This is just an example for the sake of a numerical computation, but in any real system, I will not have a sequence with complex terms. But this is just for learning or observing the result. So I need to compute, let us say, the 4-point DFT. Let me place it, and then I need to put my values, and that is say 20, 4 minus 5j, 10, and 4 plus 5j. And let us do this. When I do the multiplication, I'll get a result, but let me take the help of MATLAB in computing. So I have my xn given by 20, 4 minus 5j, 10, 4 plus 5j. This is my input given 24 minus 5j, 10, 4 plus 5j, and I want to compute the DFT of the sequence, the 4-point DFT of the sequence xn 4-point. So let me see what is my x of k. I'm getting the result as 38, 0, 22, 20. So my result is 38, 0, 22, 20. This is my my example. Let me take one more example for computing a 4-point DFT. Let us say x of n. Another example, say x of n is say 20, 3 plus 4j, 5 minus 4j, 6 plus 8j. And let us try to compute the 4-point DFT of this sequence. So 20, 3, 4, 5, 4, 6, 8. So let me try to compute. Now I'll directly try to evaluate using MATLAB. Now my xn is 20, 3 plus 4j, 3 plus 4j, 5 minus 4j, 5 minus 4j, 6 plus 8j. This is the sequence. 5 minus 4j, 6 plus 8j. This is a sequence. And 20, 3 plus 4j, 5 minus 4j, 6 plus 8j. And let me try to compute the DFT of this sequence xn and say the 4-point DFT. And let's see the result. What's my result now? 30, 34 plus 8j, 11 plus 7j. So my result is 34 plus 8j, 11 plus 7j, 16 minus 16j, and 19 plus j. 19 plus j. So now we have taken 3 examples, all are 4-point DFT, and let us see what is the observation that we are able to make. Let's take the first example. What is the first example that we took? We took a sequence that is all real, 4, 3, 2, 1. And when we computed the DFT of this real sequence, what did we get? We got a result, the 4-point DFT, such that there is some symmetry. So here we have 2 minus 2j and 2 plus 2j. There is a complex conjugate symmetry existing in our result. Then we took one more example wherein my input sequence is having complex terms. My input sequence is again having certain complex conjugate symmetry in my input sequence. So I have a term here 4 minus 5j and here I have a term 4 plus 5j. And when I have this symmetry in my input sequence, I computed the 4-point DFT, and what I got is I got a real sequence. And here I have taken a sequence which does not have any conjugate symmetry. I've just taken some sequence which has even complex terms present. And when I did the 4-point DFT of this sequence, what I got is I have got a result wherein my result, the DFT is also complex. So we have taken examples of 4-point DFT. Now let us say similarly, if I want to compute moving further, let us say we want to compute an 8-point DFT. Say we want to do an 8-point DFT. We want to compute the 8-point DFT. And in this case, what happens to my x of k? My x of k is given by sigma n equal to 0 to n minus 1. N minus 1 becomes a 7. X of n e to the power of minus j 2 pi n k by 8. So now what I will do is I will introduce the same notation of gamma. In this case, what is gamma going to be? E to the power of minus j 2 pi by 8. Minus j 2 pi by 8. And I need to compute now 7 terms. What are they? Gamma to the power of 0, gamma to the power of 1, gamma square, and so on. So let me see what is gamma to the power of 0. E to the power of minus j0, that will be a 1. And what is gamma to the power of 1? E to the power of minus j 2 pi by 8, which is nothing but e power minus j pi by 4, which will give me the value as 0.707 minus 0.707 j. I can check it. E to the power of minus j 2 pi by 8. So 0.707 minus 0.707 j. Similarly, if I do gamma square, Let's do gamma square. Gamma square is going to be e to the power of minus j 2 pi, 2 by 8, which is e to the power of minus j pi by 2, and which is nothing but minus j. Similarly, gamma cube, if I compute gamma cube, I will get it as e power minus j 2 pi 3 by 8, and that is going to give me minus 0.707 minus 0.707 j, and gamma to the power of 4 will be e to the power of minus j 2 pi 4 by 8, and that is going to be a minus 1. And similarly, if I take gamma to the power of 5, this is going to be e to the power of minus j 2 pi 5 by 8, and this will give me minus 0.707 plus 0.707 j. And gamma to the power of 6 is going to be e to the power of minus j 2 pi 6 by 8, and that is going to be a plus j. And then gamma to the power of 7 is going to be e to the power of minus j 2 pi 7 by 8, which is going to be 0.707 plus 0.707 j. And how do we remember all these values? Because all these terms can be recognized as lying on the unit circle in this complex plane. So I have a complex plane and I have a unit circle. On this unit circle, I have my gamma 0 is here. I have my gamma, gamma square, gamma cube, gamma 4, gamma 5, gamma 6, and gamma to the power of 7. So if this is my real axis and this is my imaginary axis. So when I imagine this complex plane with all my gammas, the 8, because I have taken n equal to 8, I get n samples on the unit circle equally spaced, and since we have a negative, we go in the negative direction and we get these values. So the moment I have these 8 values of gamma, I can form my 8 cross 8 matrix. 8 cross 8 matrix. So my DFT matrix X of K is given by my first row is going to be all gamma to the power of 0. Two, 4, 6, 7, 8. And of course, I have to multiply it to get my X of K. I'm going to get X0, X1, X2, X3, X4, X5, X6, and X7. What is my second row? It's going to be gamma to the power K equal to 1. For the second row, K equal to 1. So I have to go in steps of 1. Gamma 0, gamma 1, gamma square, gamma cube, gamma 4, gamma 5, gamma 6, gamma 7. How is my third row? K equal to 2. So K equal to 2. So I go in steps of 2. Gamma 2, 4, 6, 8. 8 is again 8 modulo 2. If I take, it's going to be a 0, 2, 4, 6. Next row is going to be K equal to 3. So in steps of 3. 3, 6, 9. 9 mod 8 is a 1. Then 1 plus 3 is a 4. 4 plus 3 is a 7. 7 plus 3 is a 10. 10 mod 8 is 2. 2 plus 3 is a 5. Next 0. Next row, my K is a 4. So in steps of 4, so gamma to the power of 4. 4 plus 4 is an 8. 8 mod 2 is 0. 4, 0, 4, 0, 4. Not sure if I should attempt to complete the whole matrix. So then I have 0. Next value, my K is a 5. So 5. 5 plus 5 is a 10. 10 mod 8 is a 2. 2 plus 5 is a 7. 7 plus 5 is a 12. 12 mod 8 is a 4. 4 plus 5 is a 9. 9 mod 8 is a 1. 1 plus 5 is a 6. 6 plus 5 is 11. 11 mod 8 is 3. 0. Then 6. 6 plus 6 is a 12. 12 mod 8 is a 4. 4 plus 6 is a 10. 10 mod 8 is a 2. 2 plus 6 is an 8. That's a 0. 0 plus 6. 6 plus 6 is a 12. And 12 mod 8 is a 4. 4 plus 6 is a 10. 10 mod 8 is a 2. And next, so we have come to the last row. So that is going to be 7. 7 plus 7 is a 14. 14 mod 8 is 6. 6 plus 7, 13. 13 mod 8, 5, 4, 3, 2, 1. And this is how we have built our 8 cross 8 matrix for computing an 8-point DFT. And what is the property of this DFT matrix? The first row is the first column, second row is the second column, third row is the third column. So the matrix and its transpose are equal. And just look at the last column. Last column goes in the reverse order 1, 2, 3, 4, 5, 6, 7. Similarly, the last row. So we are able to construct the complete 8 cross 8 matrix using only the 8 values, gamma 0, gamma 1, gamma 2, etc. And we have just translated the DFT expression sigma k equal to n equal to 0 to n minus 1. We have just translated that expression into this form. So all that we did was we have taken this equation. We introduced a notation for convenience in writing the terms as in terms of gamma. And after introducing this notation, we computed all the 8 terms. And remembering these 8 terms also is easy because they just are equally distributed on the unit circle and divided by an angle of 2 pi by n. N is 8, so 2 pi by 8. And so we got these 8 values of the gamma. And using these 8 values, we simply translated the DFT expression into this matrix. And this is what we have got. And so once I have this matrix, I can compute any 8-point, the DFT of any 8-point sequence. So now let's take an example. And of course, I cannot do an 8 cross 8 multiplication now. I will take too much time and I'm likely to make mistakes. So once again, let's take an help of MATLAB in computing, but let's take an example. So let us take an example. Say xn is say 4, 3, 2, 1. I'm giving a sequence of length 4. Why I'm taking this expression? Because we have just computed the 4-point DFT of the same sequence. For the same sequence, let us compute the 8-point DFT. We know that we can always compute an n-point DFT provided n is greater than or equal to the length of 4. So in this case, my length is 4 and I'm taking my n as 8. So 8 is larger than 4, so I'm allowed to compute the 8-point DFT of the sequence. On the other hand, given the sequence xn, if I'm asked to do a 3-point DFT, I cannot do. I can never compute a DFT of a sequence of a shorter length than the length that is given. So now let me go to MATLAB. Yes, so I have written a program here. So let's see what does the program do. All that the program does is it computes the 8-point DFT. So I'm creating a DFT matrix, zeros n cross n. I'm computing the DFT matrix. So e power minus j 2 pi nk by n. That's all it does, and then it also displays the matrix. It displays the matrix. Yes, and I think we have already seen this example. And let's to compute the so now let us before computing the 8-point DFT of that sequence, let us first compute the 4-point DFT of the sequence using n equal to 4. So let me take 4, n equal to 4. So I'm going to display, I'm computing the 4 cross 4 DFT matrix, and I'm displaying the matrix. And then I want to compute the DFT. So all that I have to do is I have to just do the multiplication. My sequence is x of n is 4, 3, 2, 1, and I compute the product and I'll get the result. So that is why the result also gets displayed. So let's run this code. See, this is my DFT matrix, a 4 cross 4. We saw first row all 1, first column all 1, and this is a DFT matrix which we have seen. And what is my DFT? 10, 4-point DFT of the sequence, 10, 2 minus 2j, 2, 2 plus 2j. This is an example we have already seen. Now for the same sequence, suppose I want to compute an 8-point DFT. I need to first evaluate an 8-point DFT matrix. And after evaluating the 8-point DFT matrix, I need to compute the 8-point DFT. So now to make matrix multiplication compatible, I append my sequence with 4 zeros. So my sequence now becomes 4, 3, 2, 1 and 4 zeros, and this is my DFT matrix. Let me compute the 8-point DFT of the same sequence 4, 3, 2, 1. So let's see our result. As I mentioned, the program also displays the DFT matrix. Let us look at the terms here. First row is all ones. See, it's a gamma to the power of 0, gamma square, gamma cube, etc. So we can see the terms, and this is my x of k, my result x of k. What is my x of k? So 10, 5.4 minus 4.8j. So my sequence, my 8-point DFT of the sequence, first is 10, then 5.4 minus 8.2, 5.4 minus 4.8j, then 2 minus 2j, then 2.58 minus 0.82j, 2.58 minus 0.82, 0.82j, then a 2, then 2.58 plus 0.82j, then 2 plus 2j, then 5.4 minus 4.8j is what we have. So what is unique about this result? There are two observations that we have in this result. So 2 and then 5.4 minus 4.8j. So this is what we have the result. We have computed the 8-point DFT of a sequence of length 4, and we have got the result. And how is my result? One observation that I have is I can extract my 4-point DFT. For the same sequence, if I want to get the 4-point DFT from this result, my 4-point DFT, say n equal to 4, is given by 10, 2 minus 2j, 2, 2 plus 2j. So this is an observation. So I can extract the 4-point DFT from an 8-point DFT because we are just increasing the resolution when I increase n. And in addition, I have certain values. And how is this? We find a lot of symmetry. The second term is 5.4 plus 4.8j. The last term is a complex conjugate of it. Similarly, we see some symmetry in the complex conjugate. We find a complex conjugate symmetry in the result. So see here, it is more clear here. So for second term is 5.4 minus 4.8j. Last term is 5.4 plus 4.8j. 2 minus 2j, 2 plus 2j. So we have a complex conjugate symmetry that is present in the 8-point DFT of the sequence. So now let me take one more example. Let's take another example. X of n. X of n is say say all ones. All ones. Let me take x of n as all ones and let me try to compute the 8-point DFT of the sequence. So all ones, and let me try to get the DFT of the sequence. So let me go back to my program. I will not try to display my DFT matrix because we have seen how it looks like. I want to compute the 8-point DFT of a sequence which is all ones. So what is my example now? My input is going, my sequence xn is going to be, and let's run it and let's check what's the result. What's the result we get? We get 8 and all zeros. So let's try to interpret the result. So when I take a sequence of all ones and I do an 8-point DFT, I'm getting 8 and all zeros. 4. So what's our understanding of this result? In the time domain. In the time domain, if I look at my signal n, it is all ones. It is all ones. This is my sequence xn. And in the frequency domain, x of k, all are zeros except the value at 0. So if I want to look at it from a so what is the signal which is constant for all time? It's a signal of 0 frequency. And that is what we are getting by doing the DFT. When I take a signal which is constant, does not change with time, it's a signal of 0 frequency. So that is why I'm getting a non-zero component only at k equal to 0, which is nothing but a frequency corresponding to 0 frequency. And this is going to be periodic. So once again at 8, I will get it as a 0, as 8. So this was another example. Let's take one more example for an 8-point DFT. Say x of n is say 1, 0.707, 0, minus 0.707, minus 1, minus 0.707, 0, 0.707. I'm taking a sequence xn, and this we can recognize are the samples of a cosine wave in one period. So let me take the 8-point DFT of this sequence, and let us see what result we get. So I go back to my program, and I've set my n equal to 8, so I'm getting an 8-point DFT matrix. Now my sequence xn is changed to 1, 0.707, 0, minus 0.707, minus 1, minus 0.707, 0, 0.707. And let's try to compute the DFT of this sequence, and let's see what we get. We are getting it at 0, 3.9 and 3.9, we have done a similar example in the previous module, and we got it as 4. Now I have approximated my cosine function as 0.707. So because of that approximation, I'm getting the result as almost. So I can take 3.9, 3.9, and all other terms are 0. So I have, this is my x of k, which is given by 0, 3.9, 4, 5, 6, 7, 3.9. This is my result that we are getting. And when I plot this result, if I try to plot k versus x of k, what we get is 0. At 1, I have a magnitude of almost 4, then 0, and then a 3.9. This is at 7, 1, 2, 3, 4, 5, 6, 7. And 8 is an n equal to 8. So this is the result we have got, and this result is exactly similar. So this, we have taken samples of a cosine wave of frequency 1. So when I compute the DFT, I'm getting this result. So what we have seen today is, so we can take any signal and we can compute DFT. So to summarize the learnings of today, we are given n. One method of computing the DFT is to create the DFT matrix by introducing some notation gamma, and this n cross n matrix, this matrix n cross n matrix will have only the terms gamma 0, gamma 1, etc. up to gamma to the power of n minus 1. So using these n values, I can create the complete n cross n DFT matrix. Once I create an n cross n DFT matrix, I can take any sequence, input sequence xn, perform the matrix multiplication, and I get my endpoint DFT x of k. This is one observation we have seen. The second observation we saw is when there is some symmetry, when there is a conjugate symmetry in my sequence xn, then my result is real. My x of k is real. Similarly, if my sequence xn is real, my DFT coefficient, my DFT has a complex conjugate symmetry. This is something that we have observed. And one more learning of today is, I can given a sequence xn of length say L, I can compute any endpoint DFT n larger than or equal to L, the length of the sequence. Because the greater the n value I take, I'm going to get a better resolution of my frequency spectrum. So in the next module, we shall take up properties of